So today we will talk about linear programs again. This will be the last lecture on linear programs, and on Thursday we will continue with other things. So let's see what we discussed last time. First, a few administrative questions. So please ask questions again. So whenever you don't understand something is not clear, then please interrupt me and ask questions. Slides are still available on this website. And if everything goes fine, then you can leave us anonymous feedback on Blackboard. So there will be a couple of questions. Please use it, and if something you are not happy with something or you are very happy with something, tell us. First recitation will be on Wednesday by Aditya, and he will talk about linear algebra, calculus, probability, so some basic knowledge that you will need in this class, and he will also show you another method to solve linear programs. So last time we discussed a few basic definitions. We defined optimization problems, and we were just discussing how to optimize one-dimensional linear functions, and then we continued with the generalization of these problems, and we defined linear programs where we have a linear cost function and m constraints and some constraints on the bounds as well. And then we discussed the inequality form of linear programs, and then defined the goals of these lectures is to show an algorithm, namely the simplex algorithm, that will be able to solve linear programs. We discussed a little bit the history of linear programs, and there were some motivating examples. I had some bugs in this slide that I had x5 and x6 variables, slack variables. I fixed them, so it should be more clear now. And then we had this sketch for linear programs. If you have any questions, please tell me if something was not clear that time. And then we had this motivating example how to do classification with linear programs. We had two sets, H and M, and we wanted to find a separating hyperplane. And then we had this lemma that is H and M are linearly separable if and only if there exists A n-dimensional vector and B real number, such that A transpose H minus B is always bigger or equal than 1, and A transpose M minus B is always less than minus 1. And we proved this lemma. One part was trivial, and for the other part we had a constructive proof, namely if H and M are linearly separable, then we know that there exists a C and B with these properties, and from this C and B we wanted to construct an A and another B with these properties as well, right? And how we did that we created this scalar P, and we divided C by P and multiplied by 2, and that was our A vector. And we also constructed a B scalar, and we proved that with this A and B we will have these two properties. And what's more, it will be also true that the minimum of A transpose H minus B will be 1, and the maximum of A transpose M minus B will be minus 1. And some of you were complaining a little bit about that there must be some simpler construction for finding this A and B vectors, right? So how we constructed, that was our construction, that we divided C by P and multiplied by 2. And some of you said that maybe instead of this, we should just have divided this C with the minimum over this set, right? But I'm still not sure if that's a simpler construction. You remember this last time, right? That was this discussion, how to construct vector A and B. And right, this was our construction, that we divided this vector C by this real number P. And so what was the other one? That we have this C transpose X. We know that it's always larger than B. What was the other way of constructing? What did you suggest? Dividing this C with, who suggested something? Yeah, so what was the way? Over H.
First you can find C transpose X to separate H and M.
Yes, so I have C and B that separates them. Yeah, I have C, yeah, this is how we, yeah, so the minimum C transpose X is always bigger than B in H, and B is bigger or equal than C transpose X in M.
So you find the minimum of X in H. H is the positive, right? Right.
Yeah.
C transpose X plus B.
So C transpose X minus B is bigger than 0. That's what you know.
Minus C, sorry.
So you want, instead of this, you want C transpose X minus B.
Right.
Yeah, this will be bigger than 0. We know that.
Well, then you find the minimum.
Mm.
The root over positive X.
Yeah, so you know that minimum C transpose X minus B will be bigger than 0, and you want to divide this whole C with that minimum.
If it is less than 1, you just scale it.
So you just know that it's bigger than 0, say 0.01.
Yeah, then you times 100.
So you divide.
You record a number of 100. And for those in M,
So I divide.
max is in between 0 and -1. You scale the same thing, and you take the max of the two scales.
So wait a second. So I have. So tell me what will be your C. So you have to construct a C and a B, right?
Right. First, you record number of minimum of C transpose X minus B for all those X and H.
So say that's. How to denote, say D.
Right. Let's see. And for the max of X in M,
Yeah, max.
C transpose X minus B. Right, that's the max of all the negative.
Yep.
No,
Oops.
that's smaller. For X in M,
Wait a second. Oh, I lost it. So we know that this, right?
right, you know it as let's say E. So E has to be smaller than 0, right?
Yeah, or 0.
So you discuss by cases. If D is less than 1, right? Let's say B
Mm-hmm.
is 0, 1. The minimum scale is 100, right?
Yeah.
Let's say E is minus 0.01, 0.02.
Yep.
If it's like a point 0.02, fine. Then the scale for E is 5. And you take max of 105.
Mm-hmm.
You just take 100. You scale both. Now you have 100C and 100B.
Yeah.
That's the hyperplane you want to construct.
So your C would be 1 over D times, your A, new A would be 1 over D times C, right? And your new B would be 1 over D times the old B. Right? Yeah, so in this case, so why I'm saying it's not simpler than the previous one. Oops, let's go back. So if you set up, so you need to calculate these two things as we calculated for P. But instead of, so here we do a subtraction, and you take the minimum of these two things.
Well, then the computational thing is the same. It's kind of even nice.
Yeah, computationally they are the same, right? So I'm just not saying that your method is simpler than what you suggested. Okay. And the other benefit of using this, that in this approach, you can set up the margin exactly to that value that you want, right? So this case, there will be a point where A transpose X plus B is exactly 1, and A transpose X plus B is exactly minus 1. And the margin here will be 2 if you use this method.
So that won't work if E is equal to 0 is.
Yeah, and there are other problems if that's 0, for example. Right? Okay, so let's move on if this is clear for now. And then we discussed that this linear program would solve the classification problem. And then we discussed how to transform any linear program to standard form, where on standard form we mean this, that your goal is to minimize C transpose X such that AX is B and X is non-negative. That's very crucial. And we will also require that B is non-negative as well. Okay? And we discussed how to get rid of negative variables and so on. And this is where we stopped last time. Questions? Any questions? Everything is clear? Good. So here is a problem. We want to minimize this cost function, 2x1 plus 2x2 plus 2x3 plus x4 plus 4x5. I denote the cost function with z, and we have some constraints. And we know that all these 5 x variables, they are non-negative. Okay, our goal is to solve this problem. This is a linear program in standard form. So what to do? What we will do is we will use the pivot transformation, where pivot means that you choose a non-zero element, say this 3, and we do a pivot there, on which we mean that we divide this equation by 3 and then subtract this equation from the other equations so that the coefficients of x4 will be 0 in all other equations. Okay? And in other name, this is called Gauss elimination. Right? So, for example, if we have this problem, then so we choose 3 times x4, and we divide this equation by 3, right? So what would we have then? Oops. So it would be like 4 over 3 x1 plus 2 over 3 x2 plus 13 over 3 x3 plus x4 plus x5 over 3. This is 17 over 3. And now we subtract this equation from this and this, so that the coefficients of x4 become 0 and 0, right? So this, we have this equation, and this is what we would get, that 2 minus 4 over 3 x1 plus 2 minus 2 over 3 x2. If I make a mistake, please correct me. x3 plus 0 times x4 plus 4 minus 1 over 3 x5, and this is z minus 17 over 3. And we do this for the third equation as well. Let me know if I make a mistake, otherwise we will be in trouble. Right? So the benefit of this, that now the coefficients of x4, 0, 0, and 1. Okay, so this is what happens after if we simplify the equations. So we have this new system, and you can see that we have the coefficients of x4, 0 here, 1 here, 0 here, right? And this is called pivot transformation, and after pivoting we got an equivalent system, that is the solutions, they are the same here. So, and we can repeat this, we can do another pivot, say here, x2 over 3, and then I don't repeat the calculations. But this is how it should be done, that to get one coefficient for this, we need to multiply this equation by 3, and we need to multiply this with minus 2, this equations, and add to this equation to get 0 coefficients for x2 here, and we need to multiply this with minus 4 and add to this first equation to get 0 coefficients for x2 in the first equation. Is it clear? Who cannot see what we are doing? Who can see it? Good. Okay, and if you do the calculations, then you would get something like this. Okay, so now what you can observe is that we have 0, 1, 0 for the coefficients of x4 and 0, 0, 1 for the coefficients of x2. And this is what we call canonical form. So we say that this new equation system, star, is in canonical form with respect to variables minus z, x4, and x2. We say that x1, x3, x5, that is the other variables, they are so-called independent non-basic variables. And minus z, x4, and x2, they are so-called dependent or basic variables because they can be expressed with the other variables. Okay? So the benefit of this that if we set the non-basic variables to 0, then we get values for the basic variables. Right? So you can see that if we set x1, x3, x5 to 0, so x1, x3, and x1, x3, and x5 to 0, then you can see that minus z is minus 11, so z is 11. Right? And you can also see that the basic variables x4 then would be x4 would have value 3 if all the other variables are 0. So x1, x3, x5, 0, then x4 is 0. And again, if x1, x3, x5, they are zeros, then you can see that x2, what would be the value of x2? So x1, x3, x5, they are zeros, then what's the value of x2? 4. Good. Right, so that's why we like this so-called canonical form, because it's very easy to get values for your variables. So you can set your non-basic variables to 0, and then you can read the values of the basic variables very easily. Yes?
So does the elimination ordering matter? Like how you define which variables?
So right now, all I'm saying is just you do this elimination and randomly. You just want to get this canonical system. We are not, later we will see how to choose the order, but for right now I'm just saying that if you have this canonical system, then it's very easy to read to get a solution of your system, right? But you are good that we could have done other pivots. So for example, we could have chosen x1 and x4 for pivoting, and then we would get a solution that's I calculated this at home, then z would be 3, and the basic variables would be x1 is minus 4, x4 is 11. The non-basic variables, of course, would be zeros. And what you can observe that it's not even a feasible solution, right? Because x1 would be minus 4. And we are looking for a feasible solution where all the variables, they are non-negative, right? So at some point, the only important thing is that you can set the non-basic variables to 0, and then you will get some values for the basic variables. It might be not feasible. Other questions? Okay, so the goal of pivots is just to reduce the original linear programs to a canonical form, because then we can we can very easily read the solution, and that solution called basic solution, where the non-basic variables are zeros. And as we discussed, this basic solution might be not feasible because we have these constraints that all the x variables, they are non-negative. And of course, this solution, that what we get, this basic solution, might be not optimal either. So what we are going to do with the simplex algorithm is to choose the pivots in such a way that the solution will be always feasible, and at some point we will get to the minimum of the problem. Okay? So here is a formal definition of the canonical form. we say a system of n variables, say xj. So we have n variables, x1, x2, and so on, xn. This is in canonical form with respect to some other or some subset of these variables, say xj1, xj2, xjm variables. When if and only if xji has coefficient so if so let me give you a concrete example, then it's easier to see. So in this concrete example, these variables minus z x4, x2. So this system here is in canonical form with respect to minus z, x4, and x2. And we need that xji. So for example, so this is xj1, this is xj2, this is xj3. And we need that, for example, this xj2, that the second equation for x4, it has coefficient 1 and 0 in all other equations. Is it clear? Yeah, question?
So yeah, so the standard form of the linear programming that we talked, we had a matrix A, right? So
Oh, yeah.
Matrix A is a 2 by 5 right now. So are we saying that the number of dependent variables is basically the rank of the the column rank of matrix A plus 1?
Yeah, so we added the cost function to this system, and in that we did this in such a way that the cost value is minus z. So it just extended the rank with 1, right?
Basically, what I'm asking is that it's no incident that we have 3 dependent variables in this
Yeah,
case.
yeah, exactly. Because, yeah.
We could have 2.
Yeah, so
One.
let's assume for now that this system has full rank. Okay, good point. Otherwise, we would be in trouble. So I want, if we have m equations, I need m. So I need m variables here. Other questions? So is the notation clear? So I say that this is xj1, this is xj2, this is xj3, and we need, if this is, so x4 is xj2, then the second equation, in the second equation, x4 has to have coefficient 1, and in all the other equations, it has to be 0. Right? And let's have an example. So I can just rewrite this equation this way, that identity matrix times these basic variables minus z x4 x2 plus the non-basics. And this is -11, 3, and 4. Right? And you can again see if x1, x3, or x5, they are zeros, then we can see the value of z will be 11, x4 is 3, x2 is 4. So this canonical form can be rewritten in this way as well, using matrix notation, that identity matrix with size m times x be the basic variables plus a matrix A times the non-basic variables xn, and this is vector B, right? So I just rewrote this equation using matrix notation, and I got this one. Questions? So the basic solution, the formal definition is just we set the non-basics to 0 in the canonical form. So for example, if the basic variables are, say, x1, xm, the non-basics are the others, xm plus 1, xn, then we can see the basic solution would be, well, x1 is b1, x2 is b2, and so on, xm is bm, and all the others, xm plus 1, this is 0, and xn is 0. And this solution is feasible when? So what was the constraint for the feasible solution? That all the x variables, they are non-negative. So when is this solution feasible? When vector b is non-negative, right? Everything is clear? Good. So after this, we can start discussing the simplex algorithm. The simplex algorithm has two phases. We will start with the second phase, which already assumes that you have a canonical form with feasible solution, and you just want to get a minimum value for your cost function. Okay, so assume we have this canonical form with the basic solution. So it looks like this. Right? So we have cost function minus z, cm plus 1, xm plus 1 plus, and so on, cn times xn, and this is minus z0. And we have some other basic variables and the left here, and we assume that all these b1, bm, they are non-negative. We also assume that the x variables, they are non-negative as well. So this is a starting form in a canonical form that the simplex algorithm will use. And now the question is, if we have this form, then how to choose variables x1, x2, and so on, xn, such that the cost function z will have minimum value. Okay, so using matrix notation, I could just rewrite this So, right? So this system is the same as this. And on the right-hand side, we have minus z0 and vector b. Okay, and in this canonical form, of course, the basic solution is z0 and what's xb? So we know that xn is 0. So then what will be the value of xb? B, exactly. Right? So that's what we know. And again, this is feasible. If and only if B is non-negative. Okay, so let's continue the example that we started. So again, here we already discussed the basic feasible solutions. Right? That's z is 11 and xb is x4 and x2, and their value is 3 and 4. And the non-basics are 0. And our goal is to minimize z such that xi is non-negative. Okay, so now I think it's time to have a 5-minute break, and this is where we are going to continue the second part. Meanwhile, you can think about how to minimize z. So our goal is to minimize z such that all those x variables, they are non-negative. And the coefficients in the cost functions, they are called relative cost factors. Cost factors because they are part of the cost function, and relative because whenever we will do pivot, then these values change. And what we can observe is that the coefficients of x3 is negative. Right? It's minus 5. And it might, we will see that it means that because the coefficients of x3 is negative, it means that if we change x3 from 0, we increase its value, then we can decrease the value of z. So currently, the value of x3, this is 0 because it's a non-basic variable, right? So what we do is that we keep x3 and the basic variables as parameters, and the other non-basic variables, they remain 0. And now this is what we have, that the value of z, we can see that is 11 minus 5 times x3. Right? Because x1 and x5, they are zeros, and the coefficients of x2 and x4, they are 0 as well. And now we can see that we can get a smaller value for z if we So its original value was 11. But if we increase x3, then the value of z will decrease, right? So z is defined by this equation. 11 minus 5 x3. So if I increase x3 from 0 to a bigger value, then the value of z will be smaller. So the question is how big value x3 can have. So if I would say x3 is infinite, then they would be very small, right? But we have constraints, and the two constraints we have is one that x4. So what's x4? x4 is 3 minus 3x3, right? x5, this has value 0, and x1, this has value 0 as well. And we have another constraint for x2, that x2 is 4 minus 2x3. And the two constraints we have, that they have to be non-negative. So we have to increase x3 from 0 to such a value that it's maximum, so the z will be minimum, but it satisfies these two constraints. My alarm is still on. Right? So this is what I just wrote here, and we can see that x3, when x3 is 1, that's the best in this case, because when x3 is 1, then x4 will reach 0. So x3 cannot be bigger than 1. If we just had this second constraint that x2 is 4 minus 2 times x3, then based on just this, x3 could be larger than 1, but we have this other constraint that doesn't allow this. So in other words, we just need to calculate the ratios. That is, 3 over 3 is less than 4 over 2. That's why the active constraints is coming from this equation. And it means that we will set the value of x4 to 0. In other words, x4 will go out from the basic variables, and x3 will come into our basic variables. And in this way, we minimize, z got a smaller value. How clear is this? So that's a crucial step in the simplex algorithm. If you understand this, then you understand the whole simplex algorithm. So again, we had basic variables and non-basic variables. If a relative factor is negative, then we can increase a non-basic variable such a way that the value of z will decrease. And how much can we increase that non-basic variable from 0 to a positive number? Well, that's defined by these constraints. Is it clear? Who got lost? Who? Yes?
I just want to know if you got more variables, is it in other cases, are you still going to have a good shape, like the x4 equals 3 minus 3x3 larger than 0? I mean, do you always get these kind of simple equations in other scenarios?
So we will, yes. So the answer is yes. When later you will see that indeed this is the case. So it's always very simple.
So this case is general.
Yes. Yep.
So what's the geometric interpretation of this?
So the geometric interpretation is that we had some basis basic variables, and you can think of that they define hyperplanes, and the intersection of those hyperplanes, we are in that corner. And when a new one non-basic variable became basic variables, it means that we changed the basis. One vector came in and other vector went out. And in other ways, you remember that we sketched the linear programs? Now we move from one corner to another corner. And this is how we are wandering. And we have always just moved to a neighboring corner. And we want greedily decrease the cost of Z. Okay, so this is exactly what just happened, that we had this system here. In the old system, the basic variables were x4 and x2, and the non-basic variables were x1, x3, and x5. And now we got a new system, x3 and x2. And these are the new non-basic variables, x1, x4, and x5. And this is exactly what happened, that we moved from one corner to another corner. And we can see that we brought x3 into the basis, and we decided that x3 is coming in based on the cost function, that the relative cost factor of x3, that was negative. So we decided that x3 will come in, and either x2 or x4 could go out. And we checked this ratio. And based on this ratio, we decided that x4 goes out. Oh. I think it's, if I plug this in, that helps. Maybe not much. It's in now. Other question? Okay, so we choose x4 to go out because that minimized the most. And you can also check that this is the same as making a pivot in 3x3. So again, we checked the relative cost factors. It was -5, that was negative. So we decided to do pivot either here or here. And based on this ratio, that 3/3 is less than 4/2, we decided that x4 is going out. In other ways, we do a pivot here. Okay, and you can just check this. If we do pivot here, so it means that we divide this equation by 3, and we set these values to 0. Then this would be the system. I just skip these parts, okay, but you believe me in this, right? Good. And now you can check that, so x3 came in, x4 went out, and you can see that the new value of z will be 6, because it's -11 plus 5. And of course, the new non-basic variables will be x1 and x4 and x5, and the basic variables is, you can see x3, it has coefficient 0, 1, 0, and x2, 0, 0, 1. And now you do the same thing, that we have this new system. We minimized the cost function, so now from 11 it went down to 6. And we can again check if there's a negative relative cost factor, and we can see that C5 is negative. So we need to make a pivot again, either here or here. And we do the same thing, that we compare the ratios of this divided by this and this value divided by this value. Okay, so this is what I just did here. So we do pivot either here or here. Now, because this is negative, x5 will go to the basic variables and either x2, right? So our current basic variables are x3 and x2, and either x2 or x3 will go out. And we do the same thing, that we set x5, because that's coming in, and x2 and x3 because they are the basic variables as parameters, and do the same thing, that now the value of z will be 6 minus 2 over third x5, and the value of x3 will be 1 plus 1 over 3 x5, oops, and the value of x2 will be, so you can see, 2 minus 8 over 3 x5. Clear? So we just repeat the same steps that we did before. Okay, and again, the question is, what would be a good value for x5? So it was 0, but now we increase x5 from 0 to a positive number in such a way that all these constraints are satisfied. So now you can see that x3, it's very easy to satisfy this constraint, because even if x5 is infinite, it's non-negative, and then the value of z would be minus infinite. But we have these other constraints with x2, that is, if I increase x5 from 0 to some positive number, then x2 would become negative, and that's not feasible. Right? So based on this, we need to set the value of x5 to 3 over 4, because then x2 will become 0. And in other ways, now x2 will go out, and x5 come in to our basis. And there's another lesson here. So imagine that here in this column, all the coefficients would be positive. Then what would have happened? Yeah, then we could get minus infinity for z, right? Because I just need to set x5 to infinite. The solution would be feasible, and the value of z would become minus infinite. Right? So using these steps, you can check if the optimum value of your cost function is minus infinite or not. If ever this happens, it's minus infinite. Yes?
So if it set the x5 as 3 over 4, then x3 would be bigger than 1.
So if I said if x5
As 3 over 4, right?
yes.
So x3 would be bigger than 1.
Mm-hmm.
So we concluded in the last canonical form that x3 cannot be more than
Oh, it's changing. No. So you,
It doesn't matter.
it doesn't matter anymore.
Okay.
Okay, so you just check these. Okay? So it can also happen that, say, a variable went out. At some point, it might come in again. Okay? Okay, so this is just what I said formally that if the coefficients, that is these coefficients a1, 5, so this is first equation, second equation, and the fifth variables, if they were all negative or 0, then the value of z could be minimized to minus infinity. But in our case, there was one variable that was positive, so we decided to do pivot here, and it just means that x5 comes in and x2, because we did pivot in the second equation, x2 is going out to be non-basic variable from the basis. Okay, and now if you do these steps, then you will get this system here where you can see that the new value of z will be minus times, so the negative was of minus 6 plus 2 over 4, that's 11 over 2. And you can also read the new value of x3 and x5. Yes?
x5 equals 3 over 4, the minimum of p will be 11 over 2.
So,
For this case, the minimum of p is 11. What's the difference between these two?
so can you repeat the question? Let me go back. So I'm here,
On the previous slide,
previous.
here in this case, the minimum of p is 11 over 2. If x5 equals 3 over 4, the minimum of p is 11 over 2.
So if x5 is 3 over 4, then this value will be 6 minus 2 over 3 times 3 over 4. That's 6 minus 1/2.
Yeah, but in the previous example, I think it is the same question. The minimum of z is 11.
Yeah, 11, then we set it to 6, and now we set it to 5.5, right? So we started from 11, we did one pivot, it got 6, and now it's 5.5.
Okay, that's okay. 11 is not the optimal.
No, so we just started from a feasible solution, and now our goal was to improve it. Other questions? Okay, and if you, yeah, so just the key components of the simplex algorithm is that you do an optimality test. So you check if the basic, if all these relative cost factors, they are non-negative or there's one component negative. If they are all non-negative, then you say that the basic feasible solution is optimal. However, if there's one component that's negative, then you can choose that column to do a pivot there. And in each step, one variable will come in and one variable will go out. You just choose which variable will come in. And you have to set that value from, so you increase that value from 0 to such a value that that your solution has to be feasible. Right, so we started from this feasible canonical form. The feasible solution was that the base xb was b and the non-basic variables were all zeros. And here are the formal steps. That in the first step, you want to find that column S that minimizes the relative cost. So that's denoted by CS. That's minimum of all the relative costs. If they are all non-negative, then you report this basic solution as optimal and stop. If there's a negative value, then S will be index of the incoming variables. In the last example, that was 5. Then you test for unbounded Z. So you check the values of the S column in matrix A. If they are all 0 or negative, then as we discussed, then the optimum value will be minus infinity. However, if there's one, oops. If there are positive components, then you calculate this ratio here. That is what's the minimum of BI over AIS, where AIS runs only among the positive numbers in the S column. So you decided that the S column comes in. You calculate this ratio in the you calculate this ratio, and you choose the minimum value. And we will pivot in this place. Yes?
I have a question regarding this. So it seems not necessary to really choose the pivot to replace.
Mm-hmm.
Right. So because you're looking at the non-negative coefficient R.
Yeah.
But the amount, the increments
Mm-hmm.
is literally allowed here, here, and times that.
Yeah. So very good question. So you have
And it should be arbitrary order, like anything.
exactly. So there are two things. One is that in the cost factors, we choose negative ones. There might be many negative ones. You can choose any of them.
Right.
That column will come in. That will be the incoming variables.
Not necessarily greedy.
You don't need to be greedy there. You can choose any of them. And then you have this rule as well here that you choose according to this rule. And why we use this rule? Because in this way, the B will be feasible, the new B. So the new B vector that after pivot, that will be non-negative as well. That's why we chose this. Okay? Right, so it's very easy to see. So after pivot, the J's value of B will be the old value of B plus this expression. So R is defined by this. And you multiply this equation. So this is just from the pivot. It's very easy to verify that that's the rule. And now you can see if we choose R according to this rule, then this new B tilde, that will be non-negative. So its proof is really just these two lines. So if AJS is non-negative, then because ARS by definition is positive, then this is non-negative. And if AJS is positive, then this expression has to be non-negative because we choose R according to this rule that R will be always less. So the BR over ARS will be always not bigger than this expression here. Who got lost? Is it clear then? Good. Right, so these are the crucial steps really only, that you check your cost factors. If there's a negative one, then you can choose that column to come in. and which goes out. That for that you can use this rule. And in this way, the new B vector will be non-negative, so you can continue the whole process, and you will always get feasible solutions this way. Okay, and this will be the new value of our cost function. One thing that we can notice is, though, that if the B R, if it was 0, then there's no change in Z. Right? So it might happen that you do a pivot and your cost function doesn't change. And that's a problem, because it might happen that if you do this pivot, then you go to a basis, your cost function doesn't change, and you do you can go back to a basis set where you have already been, and you would get to a loop. So you need to handle that. And there are some rules for that, how to handle. One is the so-called blends rule, where they just say if the cost function doesn't change, then you can choose that column where the index is smallest. So there was this question that if we have many negative column vector, then we can choose any of them. You can be greedy, but this rule just says that don't worry about the values, just choose that one where the index is the smallest. And the same for the outgoing variable 2, that just choose that column of the outgoing variable that's eligible column and that has the smallest index as well. And in this way, you will not get into loops. Okay, and here is a theorem that's important to us, that the basic feasible solution is optimal with total cost Z0 if all relative cost factors are non-negative. So we have this simplex algorithm rule that if all so we have this basic feasible solution, and if all these cost factors they are non-negative, then it's a global optimum. And this is very easy to see, right? That because xm plus 1, xj, and xn, they are non-negative, and if these ones are all non-negative, then the global optima is if you set xm plus 1, xj, and xn to zeros. Right? So this is very trivial. Another theorem, if you assume that non-degeneracy at each iteration, so these B values, they are always positive, then the simplex algorithm will converge in finite steps. And the reason is that in each step, you improve the basis, and there are only finite many bases. You will not get into the same basis set. So at some point you have to finish it, right? So how many steps you might have at most? You have n variables, m constraints, so n choose m. You might have, maximum you have n choose m bases that you might try. Okay, another important remark with this, that if you use infinite precision arithmetic, then we can find the exact solution. No approximation is used. And later we will talk about interior point methods that are not able to do this. They can just get to epsilon close to the optimal solution. Okay, and finally, this is the full simplex algorithm. So we want to solve this problem minimum C transpose X. X is non-negative such that AX is B. And I have 2 more minutes. In phase 1, we have to find a starting basic feasible solution in canonical form. And in we can also detect redundancies in phase 1. So for example, if 3 times x1 plus 4 times x2 is 5, and c times x1 plus 8 times x2 is 10, then this equation is redundant. And we can, in phase 1, we can also detect if the equations are inconsistent. For example, if we have 2 constraints such like this, then we cannot have any feasible solution. And phase 2 is just what we discussed. So the question is, if what left to discuss, if we have this equation set, then how to find a starting basic feasible solution that has canonical form, and we can start running the simplex algorithm, the phase 2 of the simplex algorithm that we just discussed. And that's very simple. So what you have to do is only that in the phase 1, you forget your cost function, whatever you had. You don't care about that. You introduce x6 and x7 slack variables. So you introduce an extra variable for each row. And then you solve this system where your new cost function is x6 plus x7. And you have these original constraints. So in this system, if x6 and x7, they are all zeros, then you will have a feasible solution. And why you do this? Because it's very easy to rewrite this new system to a canonical form where you can run phase 2 algorithm. Right? So we have, this is what you do, and then just 1 more minute and we are done. So we want to find a feasible solution for the original system. We introduce these slack variables x6 and x7. We have this new system. We forget the original cost function. We have this new system. And I can just represent this problem in this table form. And now what you can notice is that it's easy to rewrite this to a canonical form, because you just need to subtract this equation and this equation from this equation, and then you will get a canonical form. Because this is will be a canonical form with respect to x6, x7, and the objective variable. And then you can run a phase 2 algorithm that we just discussed to minimize this. If the minimum of this is 0, then we got a feasible solution, and then from that feasible solution, you can run again phase 2 and solve the original problem. Okay, so the details are here in the slides. So you can check the steps. You just need to do pivots. And next time, we will continue with convexity. If you have questions, then visit me in my office hours, and I'm happy to answer them. Yep.
I sent you an email maybe a week ago asking about whether it's possible to